Okay, so we're going to get started here. Start up this remote. Okay, so today's class, we're going to be finishing up some material we started last time on the area of sensitivity analysis of simulation models. Again, we're in the phase of the class where we're talking about a set of techniques or methods that, another viewpoint, a set of processes that you apply with any of the three simulation models that we've introduced, types of simulation models we've introduced in the class. That is agent-based, system dynamics, and discrete event modeling. Last time we started our discussion of sensitivity analysis, I had talked about the need to examine the robustness of model assumptions with respect to stochastics commonly in agent-based and discrete event modeling, and sometimes in system dynamics, and we had seen how we could use Monte Carlo ensembles, running the model again and again and again, and computing statistics across those ensembles to arrive at some confidence that what we're seeing in terms of model results are not merely a fluke of one particular stochastic realization of one particular run associated with a specific random number seed to generate the happenstance of the events involved, but are a more general pattern. So we commonly will run dozens, hundreds, or even thousands of these ensembles associated with models. We then turned last time to sensitivity analysis, where we were looking at examination of how model results differed when we changed assumptions regarding the model. We noted that models capture dynamics hypotheses about the underlying system and how it works, and we will often want to challenge those assumptions because, after all, they're often typically just one hypothesis, and that hypothesis might not be the only one that accords with the observed data, and there might be certain factors that we have estimated for the sake of the model, certain values like the mean time someone's ill, or certain structural assumptions like that people once recovered perpetually stay recovered. We might want to question those assumptions because we might not be sure about them. At a scientific level, we might believe they may not be founded, or there might be alternative interpretations. We want to see what the results of those alternative interpretations are. We might be examining two versions of a given model, one version with certain structure reflecting one theory about how things work, and another one a different theory, and we want to understand how they compare with each other. Or it may be that certain parameter estimates are less well known, and we want to do sensitivity analyses on them to understand the degree to which that uncertainty about that parameter has bearing on the things that matter to us, namely, say, the model outcomes in terms of certain results, or which decision is better than which other one. It may be that we vary a certain parameter assumption, and maybe that parameter assumption actually makes a big difference in terms of model outcomes. But when we compare the two most favorable decision options, perhaps it has similar impact on both of them, so it shifts them both up or both down in terms of the outcome of interest. It gives higher values or lower values for both of them, and it doesn't change the fact that one of those decisions seems better than the other, seems more reliable, or seems more favorable. In other cases, a parameter assumption might have a big impact on which decisions seem most favorable. So to examine these things, we conduct sensitivity analyses, and there's a variety of types. One-way sensitivity analyses where we vary a single parameters at a time. a multi-way sensitivity analysis where we're examining the impact of changing multiple parameters. In many cases, we spend a lot of time doing parameter sensitivity analyses, and often a little bit more, with more discretion, we perform structural sensitivity analysis, changing the actual model structure and examining the consequences. For example, taking what's a single state within our state chart and making it two states, or adding a transition from one state to the other. We previously looked at, last time, one-way and multi-way sensitivity analysis in a systematic fashion. Today we're going to look at some barriers to extending that in a fully general way, and some ways that we can try to address those barriers by being clever about picking values for sensitivity analysis. I should have warned the cost earlier, but we will be using, once again, AnyLogic today, so if any of you do require recourse to a machine, they sit over there and await you on the cart. You're welcome to go get one. For those who have AnyLogic, who have a machine with AnyLogic in front of them, I would suggest that you fire it up, because we'll be opening that same model as last time, the agent-based calibration model, which will, incidentally, also be a focus of a problem on problem set 4. So it'll be a model with which you will benefit from pleasure of acquaintance. Okay. Okay. So we talked about model uncertainty and about model results, and we've gone through some of the settings that AnyLogic, some of the structures and settings that AnyLogic provides to allow us to perform sensitivity analyses on these models. So, for example, sweeping parameters over ranges of values in this case, for a one-way sensitivity analysis here with respect to this parameter. And we may see results that look like that, or indeed sweeping two parameters at the same time over what's called a multi-way sensitivity analysis, where what's done is a systematic exploration in a sort of grid. If we could put it on the board, we have a set of values for one parameter, given here as the average illness duration, the one at the top, down here, and then we have we'll put that along the x-axis, and a separate set of values for another parameter, the third one down there, the infection probability given exposure. And we're systematically exploring this grid, walking along each possible pair of values here and simulating the model with respect to that particular pair of values. So we saw that last time, and we saw the results that were secured. These results did take place in the context of stochastics as well. Hence, we have these kind of fringing effects, which are poorly visible on this screen before you, but our remote audience may see them more clearly on my screen. And so each of the 55 combinations actually had some stochastics around it. And within AnyLogic, we could capture that by having each of these iterations be accompanied by some replications, some multiple realizations. Here we had this experiment, and we could indicate to use replications, and we could use, say, 10 replications or 10 realizations per iteration, where each iteration was going through and pairing up a specific value for average illness duration, a specific value for infection probability in this systematic grid-like fashion. Okay, are people comfortable with that? Okay, this is going to be relevant again to your problem set. Okay, so the problem, so we've seen an approach that AnyLogic can use in helping us to do these so-called parameter sweeps, these systematic explorations of parameter space. And indeed, this is one of the key tools that modelers use in sensitivity analysis and as part of a component of modeling in general. the challenge in this is that it tends to scale poorly. Why do I say that? You could read the slide that stands in front of you, but can anyone at an intuitive level tell me why do I say this scales poorly with the number of parameters with respect to which you're trying to examine sensitivity?
Power function?
Yeah, exactly. So we get a combinatorial explosion. So, you know, with just a single line, let's suppose, for the sake of argument, that with a single parameter we want to divide it into 10 different values, right? So we have a single line here, and we'll examine 10 different values with respect to it, and that's for a single parameter. If we go to 2 parameters, how many combinations of values are there? Sorry? 100, yeah. And squared. Suppose we had 3 parameters. So why 100? Well, for each value of of parameter A, we have to examine all possible values of parameter B, right? So the first value of parameter A, we have to examine 10 values of parameter B. Second value of parameter A, 10 more values of parameter B. In this sort of hideous progression, which leads to 100 combinations. How about 3? Suppose we have 3 parameters. How many combinations? 1,000, yeah. Perhaps it would be simple to think about, suppose each parameter we're associated with only 2 possible values, 1 and 0. Okay, so we'll have parameter A, parameter B, and parameter C. As to the number of combinations, let us count the ways. So, well, those from computer science background and with computer engineering exposure will recognize binary counting, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, right? Yeah. Should have enjoyed a better forethought. 1, 1, 0, and 1, 1, 1. Okay? How many values? 8 values. 2 times 2 times 2, right? 2 for the first, 2 for the second, 2 for the third. 10 values, 10 for the first, 10 for the second, 10 for the third. So in general, it rises as if we have n parameters that we're sweeping, and suppose, without loss of generality, we'll assume 10 values for each. We have how many possible combinations? If we have n parameters with 0 parameters, only 1 possible. We'll just run the model once, that's it. 1 parameter, how many possible values? Man, I guess I'm not the only one who didn't get enough sleep last night. How many possible values with 10 parameters? 10, thank you. 2 parameters, how many possible values? Oh, sorry, my head's in the way. Yeah, so 100 possible values with 3 parameters, 1,000 values. And in general, if we have 10 for each 10 possible values for each parameter, 10 to the n, right? If we have c possible choices for each parameter and n parameter of c to the n, that explodes. It gets really big very fast. It grows, you can think of it geometrically if we view it as discrete. We use the word exponentially if we view it from a continuous perspective. And once you consider, say, 6 parameters, we're talking about a million possible combinations, even if you examine each one only with 10 possible values. And you can imagine with an agent-based model, that's going to be extremely expensive because for each of those possible combinations, you might want to run 10 additional realizations for each to deal with the stochastics. And then the model itself might take a while to run because there's a lot of moving parts in the model itself. And so we've got a very heavy computational load coming out of it. It's not prohibitive for some problems. If it's small numbers of parameters, you can do it. But at some point, we need to be really quite intelligent about picking our results. Now, there's different levels of insight and cleverness that you can bring to bear. And the one that I think is most, one of the most deep, substantive, beautiful, is actually rooted in dimensional analysis. Those of you from physics background who sit in the audience, you'll sometimes find in the physics world that people routinely look to the dimensions of quantities for guidance. There's a long history in physics of deriving insight into how a system might behave, or the so-called constitutive relationships of the system, how parameter A relates to parameter B, or what have you, or variable A to variable B, by looking at dimensional structure. What are their associated dimensions? And it's a long and storied and very powerful history. But one of the most powerful things we can do with this is we can identify, if we have, let's suppose, 10 parameters that we're interested in, by doing a dimensional analysis, we can in some sense find the natural parameters, or a natural set of parameters for that system that are natural in the sense that they're dimensionless. If we have time, and I'm hoping we will, we'll come back to this point. But ladies and gentlemen, the universe, there's a conviction among many that how the universe operates is independent, that the universe operates independently of our choice of unit systems. If Canada were to revert to the imperial system of units, or the United States were in a fit of open-mindedness to adopt the metric system, inches now, inches forever, then it wouldn't change the fundamental behavior of the universe. However, the universe's processes must be amenable to a mode of description which is dimensionless, which doesn't depend on dimensions. There's a bunch of concepts packed up into there, but the fundamental issue is that if we have quantities in our model on which the processes depend, that are dimensional, that depend on some unit of time, or a unit of space, foot, or what have you. If the processes we describe in our models are dependent upon those units, then we have a dependency where if we change units, the model's constants will need to change. And for a system that's dimensionally homogeneous, in other words, if we have a system where it's consistent from a unit perspective, we're not doing something silly like in our agent-based model, adding a number of persons to persons per unit time, or adding dollars to persons, adding $3 to 2 people, which is numerically 5, but semantically meaningless. If we're not doing that in our model, if our model is dimensionally consistent, it's doing things in a careful way, it turns out it's amenable to description in a dimensionless fashion where we're using only parameter values that are independent of dimension. Now that sounds like a strong statement, but it's true. The Buckingham Pi theorem guarantees it, proved late 1800s, I think. So the basic idea is that no matter what model we build, if it's a dimensionally consistent model, if we're using dimensions, units, in in a sensible fashion. We're not doing something silly with our units. We should be able to re-express it using only dimensionless quantities. Dimensionless quantities, things that are independent of what units we use to describe them. Whether we use feet or meters, what have you, the model's calculations should be no different. Okay, and physicists routinely will de-dimensionalize the model. They'll take a set of differential equations that are expressed in dimensional terms, and they will turn into using only dimensionless quantities. And one of the big virtues of doing this, one of the big virtues is you get fewer parameters. You can describe the same system with fewer values needing to be specified. You take your same model, you formulate it in a dimensionless fashion, and now you can describe it with fewer parameters. It's the same underlying mathematics, but it can be described more parsimoniously. You've chosen your basis set, your mode of description, your pieces out of which you're describing it more artfully, and you can do so with specifying fewer numbers. For example, it may be an infectious disease model, and you have in there a count of people who are initially infected, a count of people who are initially susceptible, a count of people who are initially recovered. But maybe you don't need those 3 folks. First of all, maybe you only need 2 because it's a fixed population. So S plus I plus R equals some fixed numbers. All you need is S and I. And then maybe all you really need is the ratio of S and I. And then a specification of one of the values, for example. And it turns out by similar sort of reasoning, you can boil it down so you can get fewer parameters. We're not going to have time to cover this in detail, but I'm hoping my last lecture to you, or the last lecture where I'm covering new material in 2 lectures, will be about this, we'll expand this topic a little bit more. The basic deal is, folks, by cleverly describing your model, you can reduce the number of parameters that you need to do. So instead of sweeping 10 parameters, we can sweep 6. We know which 6. We know it's not, we don't have to sweep something over. So for Sarah's model in the back, the number of stores in the population, and the number of people in the population, and the number of regulators, we can sweep, for example, the ratio of stores to people. And by choosing those things carefully, we can actually more carefully do the experiments. We're changing only one thing at a time, and we can do so with fewer parameters. I'm not going to go into this in detail, but you should know that this is an avenue you could use, and we may see how we do it at a mechanical level. How do we find those sort of parameters? What do they look like for an actual model? We may see that in another 2 lectures. Unfortunately, I don't have time to go into it now. So that's one way, dimensional analysis. And that's the most beautiful way, the deepest way, and the way that's least trodden outside of the august domains of physics. But a second role is judiciously choosing parameters that are chosen to explore new areas of space that are deemed critically important. And there's 2 basic approaches I want to alert you to here. Latin hypercubes in orthogonal arrays. How many have encountered Latin hypercubes before? Anyone? Latin squares?
Only English hypercubes. What's the difference between a Latin and a, I don't know, Greek or English or Norwegian hypercube?
No, I can't speak to the classical roots of hypercubes. What I do know is they were first applied in the Middle Ages, where Latin was to avoid, unfortunately, to be subject to mixed metaphors, the lingua franca of the time. So Latin was the language of scholarly discourse in Europe at the time, and it may be that they earned their appellation in those times. hence they were Latin hypercubes rather than merely of English descent. Okay, so they spanned Europe in their interest and in their scholarly attention. So one is Latin hypercube. I'm surprised no one here has seen Latin squares before, because they're actually something that's trotted out in some programming contests and seen occasionally in computer science courses. Orthogonal arrays are another technology. And both of these are techniques that we see pop up in many areas of computer science. One of the areas that they come up again, which I teach about, is software engineering. If we're picking our tests to run against software, we pick them carefully using these because we can't possibly examine all possible combinations of possible things to examine. So Latin squares, this is actually one from Caius College in Oxford, England, which shows Latin hypercube. Does anyone recognize the pattern here? There's a pattern to this Latin hypercube, to Latin cube, or Latin square in this case. It has 2 dimensions, not n dimensions of n variable. Does anyone recognize the pattern there?
Particular color, it's only
Good.
one column and one row.
Exactly. That's the defining characteristic of a Latin square. Each of these colors, let's take yellow. You see there's a yellow in the first column. You see there's yellow in the second column, the third, the fourth, etc. But they're all appearing in different rows, right? Never do they appear in the same row again. Never do they appear in the same column again. The positions are cleverly chosen so that we have exactly one per column, one per row, but so it's the same as the number of rows and columns, but they are never repeating that. Okay. Now we can imagine this x-axis corresponding to one variable and the y-axis corresponding to another, and the idea here is sort of drawing on this, that we're going to run this model a single time. So we're going to guarantee that we run the model at least once for each value of A, and at least once for each value of B. But we're going to do so in a parsimonious fashion that never, needless, the idea is it doesn't repeat a value of A, and it doesn't repeat a value of B. We examine combinations of those values of A and B, not all possible combinations, but a cleverly chosen subset of those combinations. And in fact, any given one of these colors would be a legitimate Latin hypercube, Latin square sort of choice. So we could imagine, for example, for variable, again, we'll call this the columns A and the rows B, let's say, we could choose value number 2 for, in our first one, we could choose value number 2 for A and value number 1 for B, or value number 1 for A and value number 2 for B. We could choose value number 4 for A and value number 3 for B, value number 5 for A and number 4 for B. And the point is we're picking combinations. How many of those combinations? Just equal to, let's suppose, the number of possibilities for A and B are the same. Call it C. We've got just C values, but they're exploring the output of the model for each possible value of A and each possible value of B. It's just that they do so in a very parsimonious fashion. They don't ever repeat the same value of A and so on. So with just that number of colors as shown by a given color here, that's one example sort of combination of parameter values. Does that make sense to people? Now, that's a remarkable decrease in the number of possible combinations to examine. We're going down from, say, 100, if we have for each variable 10 possible choices, down to 10. An order of magnitude difference. And in higher dimensions, it can be even larger. And so with the Latin hypercube, we're never repeating
any value of a particular variable. We're exploring all possible values of it, all possible values of A, all possible values of B, but not all possible combinations of A and B, because that's very expensive. Does that make sense? Okay? And you might say, well, that's an awfully impoverished set. How do you can be confident? Well, there's a lot of things in terms of model results that might be revealed by extreme values for A and extreme values for B. Either one of them is low or very high, and that will show it to you. Still capture it. What it won't capture is kind of strange things that happen with all possible combinations of A and B. We'll be missing out on some of those, but we'll at least capture the extremes, right? We'll at least capture the things that will be triggered by any one value of a parameter. But suppose we did want to capture pairs, but not all possible combinations. There's a tool called orthogonal arrays. And the key characteristic here is, in contrast to Latin hypercube spheroids, we're guaranteed to have one choice for every possible value of each variable. So each possible value of A was represented. Each possible value of B was represented. But never was there any repeats. With orthogonal arrays, we're guaranteed to have each possible pair of values of A and B. You might say, why does that save anything? Man, if we have to examine all possible pairs, we have to examine every square in this grid. Well, for a square case, for a case of 2 dimensions, it doesn't really save us. Don't save it. But if we have 3 dimensions, or 4 dimensions, or 10 dimensions, it saves a lot. We don't have to consider all possible combinations, 10 to the 10th of these 10 possible parameter values, each of which are 10 values, let's say. Or if each of them is 20 values, possible values, each of the 10 parameters, we'd have 20 to the 10th. As the number of combinations. Whereas here, with orthogonal arrays, we're going to be guaranteeing that any 2 parameters have all possible pairs examined. Any 2 parameters we want to examine, every possible pair of values is examined there. But we're far from guaranteeing that all possible combinations of all parameters are guaranteed. It's just pairwise, every single pair is examined. Okay? And this exploits the fact that there's a lot of the issues of model behavior that are not manifested with respect to just one parameter are pairwise. So the model behaves really in a weird way, a wonky way, when we have specific pairs of values. And this sort of analysis can show it without exploring all possible combinations of values. So pairwise scales, instead of as c to the n, it's actually the maximum number of possible values of one parameter times the maximum number of another. So if all parameters have 10 possible values, it scales as 10 squared. So it's proportional to 100. If you have 100 possible values of each parameter, instead of being 100 to the 10 to explore all possible combinations, be 100 times 100. Okay. So orthogonal arrays can be defined in a very automatic, systematic, automated way, so that we can explore all possible pairs of values without exploring all possible combinations of values. Does that make sense? Okay, now, just as a point as to why this comes into software testing, because you can imagine you have in your software program a dialog box and you have different values that can be entered there. And maybe there are, radio buttons. You could choose 5 different values for each of 6 different radio buttons. Instead of examining, for each of those radio buttons, we have 5 possible combinations. We have 6 radio buttons, so 5 to the 6 possible combinations of things. We might examine all possible pairwise combinations. Okay. Okay, so here we can basically examine all pairs, and it can enormously cut down the amount of work. We still get pairwise combinations, so that all possible pairs at the square level, but at the cube level, we're only exploring things proportional to sort of what we need for a square. Okay. And for continuous variables, we break them up into chunks, into sort of ranges, and do combinations of those using each of these things. Okay. Right. So the final thing, though, I wanted to talk about. So any questions about Latin hypercubes or Latin squares? They're a good technique to know about. They enormously reduce the number of combinations. It's not perfect. We can never do perfect testing of software for realistic software testing products. And we're never going to be able to do perfect sensitivity analysis on most models. But they can let us explore some of the most important variation. Make sure we haven't embarrassingly left out, obvious cases where we have the minimum possible value for a given parameter, or the maximum possible value. Latin squares guarantees that. For orthogonal arrays, make sure we can at least examine all possible combinations. So if weird things happen for a particular combination, a pair of values of two parameters, we're at least exploring. So it helps us avoid at least embarrassingly red things that don't even pass the red face test for exploring the model. We can capture them easily with these techniques. Does that make sense? We can't aspire to true perfection here. It's just not tractable. It's not amenable to exhaustive exploration. But we can do a lot better than just seat of the pants status. Try it with a couple different values. We can systematically explore in a rigorous way that at least will alert us to many common issues. Okay? Make sense? Any questions about that? I think I'll throw in an example of an orthogonal array before I post these slides. Okay. It's drawn from a testing course, but it will give you some idea of what's in there. Okay. The other thing, though, I want to talk about is we're visited again by our friend, in my case, a dear friend, Monte Carlo analysis. And it turns out that when we have a lot of parameters, say 10 parameters, physicists deal sometimes with systems of billions of parameters, or billions of molecules in some box or something like that. In these cases, it's not so amenable to systematic exploration of all possible combinations of values. And we've seen how with Latin squares, on the one hand, and orthogonal arrays, we can reduce that. But there's another technique known as Monte Carlo analysis. And we actually saw this before, where we were using it in the context of running a model again and again and again with respect to stochastics. But here we're going to actually be drawing parameter values from probability distributions. And for this purpose, we're going to be using AnyLogic. So I'd like you to open it up, have it fired up in front of you. In a moment, ladies and gentlemen, we shall compute. Okay? So the idea here is that we're going to draw parameter values from distributions. Instead of sweeping over all possible values, we're going to draw them from distributions, and we're going to run the model again and again and again with different parameter distributions. So we're going to have some probability distribution that's derived, that's implied, that results within model outputs. Okay. So first of all, let's do this before we talk a little bit about the motivation. So, ladies and gentlemen, I think I have a slide on this. Yes. So let's double click. So we have this SAR agent-based calibration, and we have it here. And I'd like you to go to the general tab here, and I still have these sweeps enabled. So let me go and change these back to a fixed value. And then I'm going to select, ladies and gentlemen, freeform. Okay? Rather than varied in range, I'm going to select freeform. You don't even have to change the back if you don't want to. And with freeform, rather than simply saying sweep it over range, I'm going to actually impose a probability distribution. Okay? So this distribution might be more involved or simpler. It might be something like a log normal distribution, okay, with a say a log mean of 1 and a log standard deviation of 2 for the average illness duration. So what does this mean? This fact that it's, oh, I'm sorry, I have to specify a minimum, I think, by the API rules here. Let's see if I can compile this, make sure I remembered it right. So, ladies and gentlemen, what am I doing here? What's the meaning? What's the semantics of what I've just put there? Does anyone want to hazard a guess? Have I just computed the 100th Fibonacci number? What have I just done? Speak youths. Now we're in the final exam, which will be faced with this. It's better to speak now. But I can correct you. So, yes. Oh, good.
Can't see you in there.
Oh, I'm sorry. Okay. Hopefully that won't be a problem in the final exam. So what does this do? Perhaps you need field glasses in the back. What is it? Thank you. Once again, the Johnson-Troyama School is ascendant, and it is strong, and computer science is weak. Okay, so here we're basically saying, okay, when you run this model, the value to use for average illness duration, draw it from a probability distribution, draw it from a log normal distribution here with certain parameter assumptions, log mean of 1 and log standard deviation of 2 and a minimum value of 0. So here we're drawing a value from this distribution. So ladies and gentlemen, let us run this. All the other parameters are staying fixed. There's still stochastics going on at the level of the evolution of agent, for example. And here we're running the model out, and we're seeing different values resulting from, oh gosh, it's truly a pale cipher compared to what's on my screen. So, gosh, this is quite horrendous. Well, yeah. Oh, okay. Yeah, but even to my tired eyes, it's the height of dimness. So there's several things going down. I could etch them out. We have several declining trajectories here. There's actually a heck of a lot of variability, which is why it's so faint here. But you should be able to see this on your own computers. And what's going on is it's drawing the values from that distribution for that parameter. And ladies and gentlemen, that uncertainty about that parameter then induces distributions in the output. The fact that we've kind of fed in a series of draws from this random variable, this distribution for a parameter, it leads to there being uncertainty in the output. If we assume a higher value here, it's going to lead to certain resulting output, or assume a lower value, certainly resulting output. So here, ladies and gentlemen, we have a situation where we're drawing values from distributions, and Turns out you may wonder, well, why this? Well, it turns out that for reasons we don't have time to go into in detail, sorry, I'm disoriented here. For reasons we don't have time to go into in detail, it turns out to be more efficient for given, if you have a limited amount of computational resources you can bring to bear, okay? A limited amount of effort that you can put into sensitivity analysis. If you could put it into sweeps through parameter values with a certain coarseness, you instead of having, maybe you have only a certain amount, so you have 10 parameters. You can only afford to have 2 possible values for each parameter, or 3 possible values for each parameter to complete it within the requisite time. Or maybe you have those 10 parameters, and you're going to draw their values from a distribution instead. Turns out it's quite a bit more efficient statistically to sample it from a distribution, okay? To avoid sort of sweeping over it. To instead draw these things from a distribution. If we're trying to estimate, for example, the average output of this model over all possible values of parameters, rather than exploring it systematically in a grid, if we were to draw those values from a uniform distribution, just like that, we'd actually do a lot better in estimating the average value for that space. Especially if it's non-uniform distributions. If these values are clustered in certain places. We're going to be, in other words, if the parameters will tend to be clustered in certain regions of space, we're going to be doing a lot better. Okay? So it turns out these Monte Carlo methods, by sampling values from parameters, have this great advantage when it comes to computational efficiency compared to systematic exploration in a grid. Okay? It's not obvious. There's an argument from numerical quadrature that underlies this, but it has to do with some of the error scaling properties. Okay? So it can actually be, and this is something that took me a long time to fully sink in with me as an undergrad. I exhibited a certain measure of discomfort and even displeasure at the prospects. But the fact is, ladies and gentlemen, we've come to understand in computer science that there's quite a number of random algorithms, and algorithms that through brute force of randomness can actually do a better job of certain problems than the most cleverly chosen sort of schemes for iterating in a very defined fashion. There's certain times where actually randomness adds enormous value, enormous power to what we can do. And one of them is through the use of Monte Carlo analysis. We can actually save a lot of computational effort by just sort of throwing darts at a board compared to trying to explore it really thoroughly. There's some deep understanding behind that, but when it comes to exploring model behavior with respect to many parameters, you're typically going to be better off sampling from those parameter values as distributions. Better off in terms of the reliability of your conclusions than you would be if you stepped all possible combinations of them. And that, ladies and gentlemen, is a testable fact. I don't expect you to know all details of this, but that's some aspects of knowing what are orthogonal arrays or what are Latin hypercubes is a testable, are testable things. Okay, so we can draw out values from here. I will mention one other thing. There's sometimes sensitivity of a model with respect to initial state. The initial state of a model is one of those points of uncertainty that we'll often bring to bear. What state should we start in? And some models are dissipative in the sense that if that initial state, information in the initial state is lost over time. Becomes progressively less important. It's washed out after a certain amount of time. What state we were in is forgotten by the vagaries of chance and the depredations of time. Over time, we end up in kind of similar states, a similar continuous sort of steady state. This is something that engineers deal with quite a lot. They identify the steady state solution, identified with an eigenvalue of 0 of a linear system or what have you, identify the steady state solution. The vagaries of what happens initially, we term those in engineering transients. They die off often exponential rates. And that's true for some systems. But then there are other systems where it's highly path dependent. Where the systems, or history dependent is another term we use for it, where its path is highly dependent on its initial state. And systems which exhibit positive feedback, this is very common. So for example, a model associated with infectious disease outbreak can be highly susceptible to certain things in its initial state. If you start with 0 infectives or 1, it can make a huge difference. And I would argue for models of phenomena like life course of humans, where you start with early on in life has a really big impact on subsequent life trajectories often. It's not a determined thing, it's not a fated thing, but it can have a very substantive impact. Hence the attention to childhood programs, etc., with very good reason. So here, sensitivity to initial state is a feature of some models and less so of others. And it's worth testing how sensitive your model is to the initial state. I would note that in aggregate models, this can be often done a lot easier. You iterate over the number of fraction of people in each stock compared to an agent-based model where trying to quantify all possible initial states, it's infeasible. So you have to sort of just run it with different initial states, such as in a Monte Carlo type of way. Okay, so this is some common sense sensitivity analysis. Are people comfortable with that? Okay, trying to deal with some uncertainty. Okay, so with that in mind, I'm going to